Good afternoon, everyone.
Good afternoon.
Okay, so before we get started talking about chapter 7, I just want to say the same thing that I said about the first exam. I would like all of you to go into your grade book in my math lab, and next to your exam 2 grade, when you click on review, you'll be able to go through and just scroll through the exam question by question. And any question that you got wrong that was very close, like maybe it was a rounding error or a syntax error, anything where you think that you deserve some or all of the credit back, just send me a quick email. Just say, hey, Eric, will you look at the test number, number 6? If the answer was, 0.175 and you put 0.177, for example, that to me says you knew what you were doing, but there was some small rounding error, anything like that. I could go in and give you back credit for answers, because my math lab, it's very picky. It's one of the big drawbacks of the system. I really like my math lab for most things, but if your answer isn't exactly right or exactly in the form the system is looking for, you get marked wrong with no partial credit. So just let me know anywhere where you think you deserve partial or full credit. I'll go in, make changes, and give points back.
Yeah, Professor, yes, that's exactly that I want to talk to you about. When I was doing the test yesterday, I was pretty confident that at least like I had maybe an 80. And there is only one question that I left behind because I thought it was going to take too much time, and so it was one of those questions that I thought it was going to be difficult, that I prefer like to spend my time in the other questions. And when I end up and I would submit the test, I ended up getting only a 60, and I was so like devastated that I ended up closing off, and I didn't even see like the answers. So I have no way to go in and to see the answers, and I didn't save my answers. So I don't know which ones would be the ones, but I think.
Well, no, that's what I was just saying. You do, if you go into gradebook.
Gradebook, okay.
Yeah. So not the list of assignments, but if you go into gradebook, next to every homework, next to every quiz, next to every test, there's a little link that says review. If you click on review, you'll be able to see every question that was right, every question that was wrong. You'll be able to, for questions that were wrong, you'll be able to see the answer you put and also the correct answer.
Okay.
So you'll be able to go in there and analyze question by question exactly what happened.
Okay. But sometimes I think that maybe even like if you put like a comma instead of a dot, a period, you ended up like getting it wrong.
Yeah, exactly. So yeah, anything like that. If there's a comma instead of a dot, I'll go in, give you credit for it.
Okay. Okay. I'll do that then. Thanks.
You're welcome. Okay, could everyone see my screen? My whiteboard?
Yes.
Okay. So chapter 7 is the beginning of the portion of the textbook. So basically from chapter 7 through the end of the book deals with inferential statistics. So the first exam covered descriptive statistics. The second exam covered probability. And now we're starting the third unit, which is inferential statistics. So we're going to cover chapter 7 and chapter 8. And we may, probably just chapter 7 and 8. We're getting close to the end of the semester. So chapter 7 deals with estimates, and chapter 8 deals with testing claims. So a claim is any statement that involves statistics, like this, using this toothpaste will make your teeth 12% brighter. 12% is a quantification, so it's a claim. So that's what we'll do next week. This week we're just going to cover 2 sections from chapter 7, and it deals with estimates. And so, if you think back to the beginning of the semester when we started laying out the terminology, the symbols and whatnot, and as we went through, especially the first few chapters, we made the distinction in our symbols between sample statistics and population parameters. And so, for example, for the mean, we have a symbol for the sample mean and the population mean. The sample standard deviation, sample standard deviation, population standard deviation, sample correlation coefficient, population correlation coefficient, sample variance, population variance, and so on. So we've always been making this distinction between the sample statistics which we can calculate exactly, and the population parameters, which we can only estimate. And we can only estimate, let me make that a little neater. We can only estimate these population parameters because usually the population is too big to work with. So if you wanted to estimate the average height of an adult living in this country, you're not going to survey 250 million people. It's not possible. So you're going to take a sample and calculate that sample mean, and then use that to estimate the population mean. So these sample statistics, and this is a definition going back to chapter 1, we call these point estimates. A sample statistic is a point estimate. So if I say the sample mean is an estimate of the population mean, well, that's an estimate, and we call it a point estimate because it's one single value. Now, when we defined point estimates back in chapter 1, there was a couple of drawbacks. One, they're almost always wrong. I mean, your sample mean is hopefully close to your population mean, but it's normally not going to be exactly the same. And two, if you compare 2 different sample statistics from 2 different samples, there's no way of knowing which one is better. So what we're going to do is extend on that idea in this chapter. So our estimations are not going to be single point estimates. In chapter 7, we're going to cover, we're going to look at estimating the mean and the standard deviation. I mean, these methods could be used for other statistics, but we're just going to focus on the mean the mean, not the standard deviation, the mean and the proportion. And so what our estimates are going to look like are going to be some point estimate. So let's say the sample proportion rather than saying the sample proportion or the sample mean is equal to some number, it's going to look like this, an interval. So we'll say let's go with the population values. The population proportion or the population mean is going to be between some values. So let's say it'll end up looking like, 0.477 to I don't know, 501. That's what an estimate will end up looking like, or the sample mean, plus or minus some margin of error. So we'll say the population mean will be somewhere between two numbers. Let's say 76.1 and 78.2. Okay, so that's what the final estimate will look like. Not a single value or a single point estimate, but some interval of values. And the reason that our estimates will involve some interval of numbers is because there's going to be some margin of error. There's always some error involved when you make an estimation. And so these numbers I just randomly, they don't mean anything. They were just random numbers. But what our estimates will look like is going to be some sample statistic plus or minus some margin of error. Bar minus E X bar plus E. Okay, so in section 1, we'll deal with the proportion, and section 2 will deal with the mean. But this is the structure of what our estimates are going to look like. So we're going to start talking about the level of confidence of our estimates and how that affects the margin of error in our estimates. Okay. So one thing we talked about last chapter when we were talking about in the last two sections of chapter 6, when we talked about sampling distributions in the central limit theorem, we talked about the standard error. And we didn't really do much with the standard error, but we're going to come back to that concept now. Okay, so before we get into that, there's going to be some notation that we're going to need. And the first one is Z for Z-score, but when you have a subscript of some number, I'll just use alpha as the subscript. This notation means, and this is also was brought up in chapter 6 briefly, but it's much more important in chapters 7 and 8. When you see Z alpha, so for example, like if you see Z with a 0.05, something like that. Z alpha is the Z-score that separates the upper area of alpha in the normal distribution. I'll say the standard normal distribution because it's a Z-score. So for example, Z with a subscript 0.05 means, and this is something we did multiple times back in chapter 6. So here's the standard normal distribution. So when you see this, that means find this unknown z-score that separates the top 5% or the top 0.05 of the area.
And Professor Gorestin, it's like how many standard deviations is this from the mean? It's just is it 3 standard deviations from the mean?
Well, no, we don't know. Like the z-score here is unknown. So we don't know how many standard deviations above the mean.
Okay.
So this is one of those problems. Given area, find z-score. And this is something that, this was at the beginning of chapter 6 and 6.1. This is one of the types of problems that we came across. And so,
And you do this one, sorry, and you do this one with on Excel when normal dot s dot dist, and then you put a -1, right?
not dist. That's when you know the z-score. It's the inverse function when you know the area.
Oh, okay, for the area. All right.
But we can't use an area of 0.05 because that's the area to the right of the z-score. We need the area to the, Excel only works with area to the left. So if we know that there's 0.05 to the right, we know the other 95% is to the left. So we would use 0.95. And again, that's why it's always important. I say for every problem, just sketch out the diagram, label what you know, label what you don't know, and then it's a little bit more clear in terms of what to do on Excel. Okay. Another thing I mentioned in the previous few weeks when we've been covering chapter 6 is that those first couple of sections in chapter 6 were some of the most important sections of the semester because we're going to be using that stuff every section for the rest of the course. Normal distributions, areas, z-scores, those Excel functions, that stuff is really, really important because those are the tools that we have to work with from here on out. Now, in any context, not just in statistics, but if you estimate something, it's possible that you're wrong. And so we have to take that into account now in terms of our estimations. And the way we sort of quantify that is with what's called a confidence level. So all estimations have a level of confidence. So when you're doing problems in this section or in this chapter, that level of confidence has to be given to you in the problem every single time, has to be given. So the questions will all sound the same. Estimate the proportion with a 95% level of confidence, or estimate the mean with a 99% level of confidence. So that level of confidence is always given. And so that symbol alpha that I used previously, and this is the alpha we're going to use more next chapter, in chapter 8. That's what's called the significance of a claim. But the way I want you to think about this symbol alpha is the probability of being wrong. It's the probability of making an error in your estimate. And so the confidence level is going to be the complement of that. 1 minus alpha. So for example, let's look at visually the normal distribution for a 95% confidence level. But before I sketch that out, it's important to think about the idea of making a mistake, or the idea of having an error in your estimate. Well, there's two ways that could happen. Your estimate could be too high or your estimate could be too low. So half of that error should involve making an overestimate, and half of that error should involve making an underestimate. So if alpha is the probability of making an error, let's say example, 95%. If you're making a 95% confidence interval estimate, and that 95%, that's not always going to be 95, it's just one of the most common ones. It should be, you'll see anywhere from 90 to 99% given to you in the problems. What a 99 or what a 95% confidence interval estimate looks like in the context of a normal distribution. Well, if your confidence level is 95%, then alpha is 5%. If you're 95% confident you're correct, well, then you're saying there's a 5% chance you're incorrect. And that 5% probability of being incorrect is split halfway between the high end and the low end. So you could think about this as being the probability of an overestimate. You could think about this on the left as being the probability of an underestimate. And so for 95% confidence, let me make that green. Then alpha over 2. Half of alpha would be 2.5%. So that's a 2.5% chance you're incorrect by making an overestimate, and a 2.5% chance you're incorrect making an underestimate. So this accounts for the whole 100% of probabilities. 95% is your confidence that you're correct. The other 5% is split halfway between an overestimate and an underestimate. And then this would be the z-score you're looking for. Z with a subscript of alpha over 2. It's kind of tough to see that. That's alpha over 2. So anytime you're doing a confidence interval estimate, part of the process, you're going to have to always figure out what is that z-score. And that z-score depends on the areas, and the areas are coming from this, the given level of confidence that's given to you in the problem. Okay. And if there's any questions along the way, just please unmute yourself and stop me at any point. All right, so now let's talk about what that confidence interval estimate looks like. As I said before, it's going to be your point estimate plus or minus some margin of error. That's what gives the estimate a range of values rather than one specific value. The point estimate, that's the sample statistic. That's sort of the center or the starting point. And then you add and subtract the margin of error. And this margin of error, which we'll call capital E, E for margin of error, that's equal to the critical value that's that z-score up there times the standard error. Or you can think about it like the z-score, z subscript alpha over 2 times the standard error. All right, we're going to talk about 3 different estimations. So like I said, we're going to talk about estimating the population proportion and the population mean. But we're going to look at 2 different cases for the population mean. We're going to look at estimating the population mean when you know or you're given the population standard deviation. And we're going to talk about estimating the population mean where you don't know the population standard deviation. Excuse me. And again, everything I'm going through here, I go through in my lecture video that's posted on the ePortfolio. Okay, now the standard error. Which we're going to use in, so let's make a little chart here. The standard error that we're going to use in our confidence interval estimate will be slightly different. Will be different for each one of these. So I think we'll need 4 columns here. The standard error for the proportion is p hat. So the sample proportion times the complement of the sample proportion divided by n, and we take the square root of that. So that's going back to what we covered in chapter 5.2 for the binomial distribution. The standard error, and this is going back to section 6.3, the standard error, if we know the population standard deviation, if we know sigma, the standard error is sigma divided by the square root of n. That's from the central limit theorem. But if we don't know the population standard deviation, then we have to use the sample standard deviation. And I have all three of these standard errors. I have them all on one slide on my notes. Let me see if I could pull that up real quick. PowerPoint. Yeah, so you'll see as you watch my video, you'll see this slide somewhere in there. I think this looks like slide 16. Each of the standard errors. So for every single problem in chapter 7, you're going to be using one of these three standard errors, depending on if it's proportion, if it's mean with sigma, or if it's mean without sigma. Now, the distribution that we're using, well, we've only covered the one so far for continuous data. So when you're estimating the population proportion, we're going to continue to use the normal distribution and everything we covered in chapter 6 about the normal distribution. Same thing if we're estimating the mean, if we know sigma, if we know this, the population standard deviation. But if we're estimating, and so this is, let's say this is 7.2. If we're estimating the mean and we don't know sigma, well, that means there's more unknowns in the system. That means that if we don't know the population mean and we don't know the population standard deviation, that means there's two unknowns there. That means there's going to be more error involved. So we can't use the normal distribution anymore. We're going to use something very, very similar with a graph that looks almost identical. What's called the t-distribution. This is new. This is something we'll talk about today. But it works very similar to the normal distribution. And so our margin of error, which I was just talking about above. Margin of error is the critical value times the standard error. So the margin of error would be the z-score times p hat q hat divided by n under the square root, or the critical value z alpha over 2 times the standard error for the mean, sigma over the square root of n. And if we're using the t-distribution, it all looks the same. It's just going to be a slightly different number. Okay, so what I have here in red, that's the margin of error. That is the number you have to calculate in every single problem in chapter 7. With anytime you're doing an estimate. And that's the number that you'll both add and subtract from the given point estimate. All right, and this shouldn't really even be making much sense yet until we actually sort of put it into practice and work through a problem start to finish. But this is a new topic, so we sort of have to lay the groundwork first. Now that margin of error which tells you the how big your interval is, your estimate. Well, that's directly related to your level of confidence. So the higher your level of confidence, the larger your margin of error. So what do I mean by that? For example, let's say I wanted to estimate, let's say I wanted to give an estimate of the average age of students in this class. Well, I could tell you right now with 99.999999999% confidence, almost 100% confidence, I would bet my life on it, that the average age is somewhere between 15 and 50 years old. 15 and 50. Well, that's not very useful because it's such a wide range. Now, I could almost guarantee that the average age is somewhere between 15 and 50. So my confidence is really high because my estimate is really, really vague. So the more specific your estimate gets, the more likely you're wrong. So if I said, oh, well, let me change that to 22 to 28 years old. Well, I'm less confident in that than I was previously. Or if I say somewhere between 27 and 28, I'm even less confident in that because it's getting more and more specific. So the higher your confidence, the higher your margin of error. Okay, so let's do a problem. Let's see what this looks like start to finish. This is the kind of thing, well, I want to say two things about chapter 7. One, I'm just repeating what I've already said in the last few weeks. If you're feeling good about chapter 6, chapter 7 is not going to be too bad. But as I said, as 3 weeks ago and 2 weeks ago, those topics we covered in chapter 6 extremely important because we're going to be reusing them from here on out. Every section. Okay, so here's a common problem, similar to something you might see in section 7.1. A survey of 865 voters in one state reveals that 408 favor approval of an issue before the legislature. Basically, 865 people were asked a yes/no question. 408 of them said yes. That's your sample data. Now, using that sample data, construct a 95% confidence interval for the true proportion of all voters in the state who said yes, who favored approval. Okay, let me bring in a graph. There we go. It'll be neater than anything I could draw. Okay, so our confidence interval for the proportion is going to look like this. Sample proportion plus or minus some margin of error. So the first thing we need is our sample proportion. So the proportion, remember proportion means percentage. The proportion of people in our sample that said yes, well, that was equal to 408 out of the 865. So 408 divided by 865. So that will be our sample proportion. That's our point estimate. That's the center of our interval estimate. Okay, which means Q is the complement of that. So let's say equal 1 minus our answer for p hat. Okay, so this was the 408 divided by the 865, and this was the 1 minus p hat. Okay. Now, our margin of error, let me go back to blue. Our margin of error is equal to our critical value, that's that z-score, z alpha over 2, times the standard error, which is p hat, times q hat, divided by n under the square root. Okay, so we need that z-score. So going over to our normal distribution graph, we're given our confidence level. Our confidence level is 95%. So that means this over here is 2.5. This over here is 2.5. So that 95% confidence means 5% chance of an error. That 5% is split in half. 2.5% of being wrong by making an overestimate. 2.5% chance of being wrong making an underestimate. So this is the z-score we need. It's always alpha over 2 because it's half of alpha is the overestimate and half of alpha is the underestimate. So we need that z-score. That's what I was saying earlier. You have to be able to calculate that z-score. And we do that. Let's put that over here. .975. So we could do that using the Excel function from back in chapter 6. Now, Excel only works with all of the area to the left of something. So if we want this z-score, then all of the area to the left of that z-score, well, there's the 95% in here, and there's the other 2.5% out here. It's 95. That's 2.5. So that's a total of 97.5% or 0.975 to the left of that z-score. So that's equal norm dot s dot I and v with an area of 0.975. Now, this z-score, now those z-scores are usually given rounded to 2 places, 2 or 3 places. This one's usually given rounded to 2 places. 1.960, so we could just say 1.96. That z-score, 1.96, that is the same z-score that you'll use for every single problem where the confidence is 95%. So in chapter 7, if it's a 95% confidence interval estimate and you're using a z-score, it's going to be 1.96, always. So the first time you do a problem where the confidence is 90%, whatever that z-score is, it's going to be the same one for every other 90% problem. So that 1.96, that's a number you're going to see over and over. Okay, so we have p hat, that's the sample proportion. We have q hat, that's the complement of the sample proportion. We now have our critical value, that z-score, and n, well, n is given in the problem as well. A survey of 865 voters. So n is 865. All right. So that's everything we need to make that, to construct that confidence interval estimate. So now we need to so basically we need this guy. We need the margin of error. Okay, and there's four numbers in here, and we have these 4 numbers here. All right, so that should be equal to the z-score times the square root, SQRT, of p hat, which is right there, times q hat, which is right there, divided by n, which is right there. So you can see it up here on the function bar. So that is the margin of error up here. So our confidence interval estimate well, the lower end, this p hat minus e, or the point estimate minus the margin of error, that should be equal to the sample proportion minus the margin of error. And the upper limit should be equal to the sample proportion plus the margin of error. And so that's what your final answer should look like, something like this. The true value of the population proportion based on the sample results, the size of the survey, and the level of confidence. Let's say if we round to 3 decimal places, it looks like 0.438 to 0.505. Any questions so far?
The only one that I have, Professor Christine, is I cannot see like the chapter number 8 stat on my ebook yet. Is that you're gonna add that to it later on, or?
Yeah, I'll put that up sometime this week.
Okay,
Yeah, we're not starting chapter 8 till next week.
okay.
All right, so one of the things that I recommended doing back in chapter 6 was making a template for things that you're going to do over and over. And I mean, I'm not going to do that for you. That's something you should definitely do on your own. But we could talk now about a template, maybe just for this one problem, or for this, section 7.1. So here's one specific problem, but you're going to do many of them in the homework, and then again on the quiz, and then again, you're going to see it on the exam. So this exact same process, you're going to be repeating many times. So one thing you might want to do is something like this. So I'll label this confidence interval for the proportion. So what's involved here? Well, we needed P hat, that's the sample proportion. There was a Q hat. The hat is that little upside down V over the P. There's the Q hat. There was the N. And there was the Z score. Z sub, let me put an alpha in there. Alpha. There was the margin of error. Actually, the standard error, the margin of error, and then the final answer upper bound. So this looks like everything that we just worked with that last problem. All right, so what I'm looking at is all these numbers over here that we calculated and then used to get our final answer. And the color coding I used, and the last time I explained how to do this in another Zoom call, the same color coding, I use yellow for numbers I have to manually type in that are given in the problem. And blue for things Excel is going to calculate for me. So the first one was the sample proportion, and that is equal to the number of successes divided by the sample size. Okay, so that was the right here. The 408 was the X and the 865 was the N. So 408 out of 865. Excel gave us this number here for P hat. Then Q hat was the complement of that, equal 1 minus sample proportion. Our standard error is the square root of P hat times Q hat divided by N. All right, so what so this is X divided by N. This is 1 minus P hat. The standard error, that's the P hat times Q hat over N square root. So I'm just sort of typing these things into Excel. The margin of error, that's the z-score times the standard error. So for margin of error, that should be equal to this z-score, which we don't have yet, times the standard error, which is B7. Let's add one more row. So we're sort of figuring this out as we go along. So that's z-score. So I'm talking about this z-score here. We use the norm.s.inverse function. And that's the area is always going to be 1 minus the area to the right. So 1 minus alpha over 2. So this red area is 1 minus alpha over 2. So let's put that in here, equals norm.s.inverse. 1 minus and alpha over 2, I'm going to type in here. Then the lower bound and the upper bound, that's your final answer. That's going to be P hat minus E and P hat plus E. So equal sample proportion, which is going to be up here, minus the margin of error, which will be in B9. And the upper bound will be sample proportion plus the margin of error. Okay. So with this template, what I did is basically all of these individual calculations, exactly what I did here, but instead of typing the numbers in specifically from the problem, I'm just giving them a slot on Excel.
Professor?
Yes.
How do I know, like in this problem, the mean, I mean, it could be mistaken, but the mean is not given, the standard deviation is not given. How I would know to use the normal standard deviation formula?
I'm not sure I understand the question. Could you say that again?
Oh, no, I mean, I'm saying like there is a formula for a normal, a normal standard deviation inverse over here.
No, that's not what that is. That S is not standard deviation.
Oh, okay,
That's normal standard
inverse
distribution. So that
distribution.
that S is telling you you're using z-scores, not x values. That has nothing to do with the standard deviation.
Okay,
The key word in this problem that tells you that you're using these formulas here is the word proportion.
okay,
So when you see the word proportion, that means you're using all these formulas. It'll be,
okay,
the formulas are different in the next section. But you basically, when you see this, when you see confidence interval and proportion, when you see those two terms, confidence interval, proportion, that means you're using these formulas over here. All right,
okay.
so
Thank you.
in this problem, we were given the 408, we were given the 865, and we were given that if the confidence was 95%, then alpha is the other 5%. So if I go back to this template, if I type in those three numbers that were given, 408 out of a total of 865, with half of alpha being 0.025. .438 to 0.505. And that should be 438 to 505. That's the same answer we got before. Now, anyhow, I should be recording this, so I should have a video. I should be able to post a link to the video of this call if you want to go back through this process. Recording on this computer. Yeah. I recommend you do this for section 7.1, 7.2, and then again in chapter 8. It might take you a little while, but it's basically what you want to do is take what you're given in the problem, 865, 0.025. So all I had to do was take these three numbers, which I knew from the problem, plug them in here to my yellow square, my yellow slots, and Excel does all the other calculations for me. Even if this takes you a half hour to do, it will save you time in the long run. So my advice is to, if you choose to make a template like this, where you're basically, setting up your calculations for every single other version that you're going to do of this problem, the numbers change. You just change those three numbers in the yellow cells and you get your answer. My advice is use a problem that you already know the answer to. Whether it's from my notes or you could go to the textbook and, one of the examples that's worked out in the textbook, something you already know the answer to. So that way, you know that your template is working if it gives you the answer that it's supposed to give you. All right, so that's basically it for this type of problem. Now there's two main problems in this section. This is the big one, the confidence interval estimate of the proportion. The other one is, let me go back to here. So problem number one, construct a confidence interval estimate, which will look like p hat plus or minus some margin of error, where the margin of error is equal to the z-score, which is the critical value, times the square root of p hat times q hat over n. So that's what we just did. The other one is to determine the necessary sample size. So basically, in the first type of problem, you have to calculate E, which is the margin of error, given some information, including the sample size. The other type of problem, you're given the margin of error, and you have to find the sample size. Basically, how much data do I have to collect in order to be this confident and within this margin of error of my true population proportion? Now, the formula for n is the formula for E from above. E is equal to z alpha over 2 times the square root of p hat times q hat over n. Now, we could solve this equation for n. So we could square both sides. So you get E squared is equal to the z-score squared times p hat q hat over n. You can multiply both sides by n. So these n's will cancel. So you have n times E squared equals z-score squared times p hat times q hat. And then you could divide both sides by E squared. This is, I'm doing this quickly because this is not something you're ever going to have to do. This is just, instead of me just saying, here's the formula, I just want you to know where it comes from. We start with this one up here, and then solve for n. So when we get n by itself, we get n. So basically just rearranging that formula, we get n is equal to the critical value squared times p hat times q hat divided by margin of error squared. And so when you see problems involving, find the minimum sample size necessary, all, these four numbers either given or, well, the margin of error will be given, the level of confidence will be given. So you plug those numbers into this formula to find the minimum sample size. Okay, so then the first half of the next section, so in section 7.2, let me scroll up here for a minute. Okay, so we've talked about population proportion. So now we have to talk about estimating the mean. Sometimes we know sigma, sometimes we don't know sigma. Actually, in real life, we almost never know it, but in this class, some problems you'll be given the population standard deviation, sometimes you won't be. Now, as far as how to do the problems, these two are very, very similar. The only difference is you use a different standard error in your calculation. Okay, and just like before, your estimate will be sample statistic plus or minus the margin of error, just like with the proportion. So it's going to be, you could write it like with the plus minus, or you could write it as an inequality. Either way. And so we have two cases. We have the problems where you know sigma, where it's given to you in the problem. And then there's the other ones where it's not. Okay, so we've already talked about how to find this z-score based on the level of confidence. Now let's talk about how to find this t value here based on the level of confidence. Okay, I'm going to bring my notes over because I don't want to handwrite a lot of this stuff. It's a little bit wordy. Okay, so when we're estimating the population mean and we don't know sigma. We need something that works like the normal distribution, that has the same properties of the normal distribution, but it involves a little bit more room for error because we now have two things that we don't know. If we don't know the population mean and we don't know the population standard deviation, that's two sources of error as opposed to one. So this t distribution does exactly that. It works and looks just like a normal distribution, except it has a little bit more room for error. All right. Now, couple of key differences. Actually, one key difference. If you look at number 3, there is only one standard normal distribution. That's the one we've been using. It's the same graph for every problem. But there are different t-distributions, and they depend on the sample size. Because remember, you could decrease error by collecting more data. So when the sample size goes up, the error goes down. So the more the more sample data you have, the closer and closer the t-distribution is to the normal distribution. Now, this is a new term here, degrees of freedom. I'm not going to explain in depth what that means. I do so in my lecture video, which you'll watch at some point soon, hopefully. But for us, all we care about is the fact that the degree of freedom is one less than the sample size. Whatever n is, the degree of freedom, which we'll say df, is n minus 1. Let's not overcomplicate it. If we were covering chapters 9 and 10 and 11, like I normally do in a non-virtual semester, then I would dive real deep into degree of freedom because it changes for different topics. But since we're only looking at it for this one specific case, all you need to know is that the degree of freedom is the sample size minus 1. All right, so here's 3 distributions. The blue one is the standard normal distribution. That's the z-scores. The yellow and the red are the t-distributions. So you see they look very similar to the normal distribution. The red one has a larger sample size. So this is the red graph. Sample size of 12. This is the orange graph. Sample size of 3. So you see the larger sample size version is closer to the normal distribution. And so in terms of choosing the right one, I mean, basically, if you know sigma, you use the normal distribution. If you don't know sigma, you use the t-distribution. All right, so here's an example of a problem which maybe we'll work through, but not just yet. On my e-portfolio, here in activity 7, where you have a link to my lecture video where I go through my PowerPoint notes, you see here Excel functions for the t-distribution. So you have that there as a reference for when you need it. Let's see if it's going to open. Okay, so I made this just to sort of cover most of the bases. Let's see if we could fit it all. Yeah, there we go. Okay, so normal distributions, t distributions. On the left, these are the Excel functions that we saw in chapter 6. So the way the t distribution works is very much the same. All you have to do is replace the norm with the letter t. So instead of norm.s dot dist, it's t.dist. Or instead of norm.inv, it's t.inv. So we're going to be using the two-tail version. Now these t distributions down here, the only one that's relevant is this one, the one that looks like the confidence interval graph, where you're only looking at the area in the middle. We're not looking at left or right. That's for chapter 8. But so right now we're looking at this one right here. All right, so let me bring a problem over from the notes. All right, so this will be similar to the last problem we did. Okay. A football coach randomly selected 10 players and timed how long each player took to perform some certain drill. And the time in minutes is given. So we have these, oh, it says 10 players. It should say 12 players. Let's change that. Okay, so we have these 12 data values, and we want to determine a 95% confidence interval for the mean of all players and assume the population has a normal distribution. Okay, so two things. One, we're looking to estimate the mean, and two, we're not given the population standard deviation. So when those two things happen, you want to use the t distribution instead of the z distribution. Okay, I don't want to make this more complicated than it needs to be. The only difference in terms of how we use it, the only difference between the t and the z distributions is it's just going to be a different critical value. So when we use the z distribution, So let's do it like this. So in the previous problem we just did, we were given the level of confidence as being 95%, and that critical value, that z-score that we found, was 1.96. So for every single problem where the confidence is 95% and you're using z-scores, that z-score is 1.96. Now, the difference with the t-distribution is this is going to be a different number, a different critical value. So it's the same 95% confidence. Which means 2.5% error above, 2.5% error below. And now we're looking for this t value. All right, so let me copy down these numbers from the problem. 7, 10.8, 9.5, 8. You'll be able to export the data right to Excel from the homework. 11.5, 9.9. 10.5. Okay. So that's the data that's given in the problem. Now I'm inserting these symbols. This is not something you have to do. It's just for a visual aid. Visual aid with what we're doing. Okay, so we need the mean and the standard deviation of this data set. So those functions we know. The average, so that's x bar. Oh, oops, I'm putting these symbols in the wrong place. They shouldn't, sorry, they shouldn't even be there. X bar. I'm getting ahead of myself, sorry. Sample mean and sample standard deviation, STDEV dot S. Okay. So we have sample mean, sample standard deviation. Our degrees of freedom. Should be 11. Remember, degree of freedom in chapter 7 for all of chapter 7. Degree of freedom is 1 less than the sample size. So our sample size is 12 values. So degree of freedom is 11. Okay, so now we need that t, that critical value, that t value. So again, we find it in the same way we find the z-score. It's just in the Excel function, and this is a new Excel function, just replace the norm with the letter t. Okay, so that's this one right here, t dot inv. And it's just like before, area to the left of the critical value. And so just like before, the area to the left of this critical value. So we're looking for this critical value here. Area to the left was 0.975. So we're going to use equal t dot inv. Area to the left, 0.975, comma, the degrees of freedom, which is 11. And when you start typing the function in, Excel prompts you in terms of what to type inside the parentheses. So equal t dot inv. Probability means area to the left, as it always has, comma, and then it's saying degrees of freedom, which should be 11. So we get a slightly higher critical value, 2.20 if we round to 2 places. All right, and then once we have that number, we solve these problems generally in the same way. Our margin of error is equal to the critical value, that's that number we just found, times the standard error, which is s divided by the square root of n. Okay, so let's say equal that t value times the sample standard deviation, which we have, divided by SQRT divided by the square root of 12. And just like before, our interval estimate is between sample statistic minus the margin of error and sample statistic plus the margin of error. So I'll put those, let's say, okay, so these values, we now have them. So we take the equal to the, now we're using, so let me actually go back for a second. To get this interval, we're using two numbers. We're using this one. The sample mean, and we're using this one, the margin of error. So our final answer is going to be the sample mean plus or minus the margin of error. Okay, so now we've done pretty much most of the work. So equal X bar minus E. And equal X bar plus E. So we could say with 95% confidence that our sample, that our the true population mean of all players that perform this drill based on the 12 where the data is collected from, for the population of all players that perform this same drill, the average amount of time should be somewhere between maybe 8.36 and 10.84 seconds. Maybe we'll round this to a couple decimal places. And again, I would recommend, doing something like this for each individual type of problem that you'll see. And there's like there's only like 4 different types of problems you'll see in chapter 7. Estimating the confidence interval estimate of the proportion, estimate of the mean with sigma, estimate of the mean without sigma, and minimum sample size for the mean, minimum sample size for the proportion. So 5. I've done one of them for you in this video. It might not be a bad idea. Actually, it would be a good idea to do this, sort of this make a template like this for the other types of problems. Okay, I know we covered a lot, and a lot of this should not really seem very clear right now. I mean, I don't think anyone, I wouldn't expect anyone to be at a point right now where everything seems that it clicks and makes perfect sense. After this Zoom call, you have my lecture videos to watch. You have my Excel videos to watch. You have a few Khan Academy videos to watch. Once all of that watching is done and you've gone through my notes, then you should feel like you're at a point where you could start the homework. We have another Zoom call, as always, Friday at 10. But if you have questions throughout the week, please don't hesitate to send them my way. You could wait till I could wait till Friday to answer the questions. In our next Zoom call, I could set up a one-on-one Zoom call, or I could respond via email. And always, if it's an Excel issue you're having, send me your Excel file. Don't just say, hey, Eric, I'm having an issue with Excel. I can't help you. If you save your Excel file, attach it to an email, I could figure out the mistake. I could make the correction. I could send it back to you and explain to you what the mistake was. So if that happens also, please reach out. Any other questions for me while I'm online?
Well, I would just like to say that unfortunately I cannot participate on the Friday classes because I have anatomy and physiology, and there was when we chose me and my wife, we were looking through the courses, and now there was this statistic that I wanted to take, and I didn't realize that was the Friday class would not agree with my anatomy physiology class. If is that fine with you, I would participate on the Monday classes.
Well, yeah, no, of course. I mean, that I've been saying all along, if you can't make the Friday class, that's optional. You could request to have a one-on-one Zoom call with me any point during the week, or I'll continue to, for the last 2 Fridays, I've been recording and posting the Zoom calls.
Oh yeah, I saw the one for the extra credit project that you have. I'm planning to do that too. And if questions come up about that, I would.
Okay. Yeah, so yeah, that meeting was recorded, and then the last Friday where we reviewed for the tests, that was recorded. And then, I'll continue to record those Friday 10 a.m. Zoom calls. So they've
Okay.
been normally lasting about an hour. So then you could, yeah, of course, you'll have access to those videos.
Okay. Thank you, Professor.
You're welcome. All right. Any other questions while I'm on? Okay. So good luck with this week. I think this week the material is, it may start off seeming like it's a lot or it's confusing, but one thing that's nice about this chapter is that, like, once you start doing problems, once you do 3 or 4 problems, you'll see that there's very little variation. All the problems are done pretty much the exact same way. Chapter 8, that's a little bit different. We'll get to that. We'll cross that bridge next week. But for chapter 7, there's only a few different types of problems, and there's not much variation. Basically, it's just different numbers with the exact same calculations. That's why I think a little, like a template might be helpful, because if between the homework, the quiz, the exam, if you end up doing 30 or 40 problems from chapter 7, it's the same 4 or 5 problems repeated. There's very little variation. So don't, if you're frustrated in the beginning, just try to fight through that, because it's, you'll see a lot of repetition in this chapter.
So do you think it's going to be a little bit easier, because I mean, and then the last exam, I think we have 3 chapters. In the second, in this one, we're going to have like 2 chapters. At least it's going to have less work, I think.
Yeah, I think a lot of the difficulty in an exam comes with the wide variety of topics that are covered.
Yeah.
So chapters 4, 5, and 6 were all very different. So that variety definitely caused some difficulty, I'm sure. So yeah, in that sense, this exam will be a bit more targeted, and we're only covering 2 sections from chapter 7.
Yeah.
And and that's even more of a reason why you may want to make a template for each type of problem, because those templates, like the one I made in this video, they'll be really, really helpful for the exam.
Yeah, I definitely will.
With probability, with probability, every problem was different. So you couldn't take like one standard approach. And then, there was a lot of variation in chapter 6, but in chapter 7, not so much.
I've been writing all of your notes. I think I have like one of these like full notebooks just for notes.
That could be helpful. Just the act of writing it down makes it, a bit easier to recall later.
Yeah.
All right. So if there's no other questions, we could go ahead and end the call. Good luck with the week. Good luck with chapter 7. And again, if there's any questions along the way, please send them my way.
Thank you. Have a good week.
All right. You're welcome. Have a good day, everyone.
You too.
So thank you.